So in this question, we have to find the acceleration of the system if friction is neglected first, and then find the tension forces and in presence of coefficient. So then we can take care of that. Now, this is the question we have initially, where we have mu 0, right? So the external force is F. Now, masses are equal. Now, tension force. So there are two ropes here, right? So we mark T1, T2 because two ropes, right? So we should mark it differently. Then to find the acceleration of the system, what we do, we use F is equal to ma for the system. F is equal to ma for the whole system. So the force, external force for the whole system would be F, right? So that would be F, and mass of the system would be 3m system, right? So acceleration of the system we will take as A. So acceleration A is equal to F divided by 3m here. Now we need to find the tension forces. So now we have the acceleration here, right? So now the tension force is the next one. So to find the tension force, what I will do, I will draw the free body diagram. So individual forces acting on the masses. So M here, T2. Remember, always the tension force is away from the object. And M, second M. We have T2. Right hand side we have T1. For the third mass, F force, and T1 to the left. Now all of these masses are moving with acceleration A. So now what we will do, we will use F is equal to ma individually, right? So I will use F is equal to ma on this object. So that would be T2 is equal to m times acceleration. Now we found the acceleration before, equation number 1, that would be F divided by 3m. So you will substitute it here. So mm gone, so the answer would be F divided by 3. So T2 is equal to m divided by 3. Now you can use F is equal to ma here, but it's going to be long, you know. So T1 minus T2 is equal to ma. Now here you found T2, right? So you found T2, so you can plug this value over here and find T1, or you can use the other mass and use F is equal to ma. So the external force there would be F minus T1 is equal to m times A. So why I prefer this one, here you don't have, here you have two unknowns, but that's fine, we found it before, but I'm not going to play with that since I have two variables there. So from here you subject T1, T1 would be F minus ma. So F minus ma would be F divided by 3m. So you can do that. So the answer would be 2F divided by 3, that would be T1, and that's the answer. So part C talks about the same thing, but in presence of friction. So we have the same system here, F force. So now here T1 forces are different to the previous situation, 3m's. Now here you have a friction, right? So mu is the coefficient of friction. So if you have a friction, a rough surface, then we have friction forces this way, right? So you can say F1 here, F2 here, F3 here. So now how to find this friction force? So you know friction force is equal to mu times mg or mu times r, right? So F1 force now friction force, that would be mu times mg, because we are interested in the mass associated with F1. F2 also mu mg, so F3 also mu mg. Now if you use F is equal ma for the whole system, now what we have is what is the net force? Net force would be F minus F1, F2 and F3. Now that would be is equal to mass would be 3m and the acceleration would be a. Now F1, F2, F3 are equal to each other, so that would be F minus, I can say 3 mu mg is equal to 3 ma. So now from here you can find acceleration, and that would be F minus 3 mu mg, the whole thing divided by 3m, and that's the answer to that. So now the values are not given here, right? So in general I'm talking about this question. So when the values are given, it's just a matter of plugging the values into this equation and you get the answer, right? So that's how you find it. Now you asked to find the tension forces. So now we will have the free body diagram. Now this tension would be T2. So okay, here it's T2, here it's F1, acceleration is a m. For the second object m, we have T1 here, T2 and F2, same acceleration. The third mass has F force and T1 tension as well as F3 friction force has the same acceleration a. Now we will use F is equal to ma here. So when we do that, this should be T2 minus F1 is equal to m times a. If is equal to ma here, that would be T1 minus T2 minus F2 is equal to ma, and F is equal to ma to the third object, net force would be F minus T1 minus F3 is equal to ma, right? So T2 you can find from here, that would be F1 plus ma. So I'm not going to do the simplification. Why? It's going to be a humongous simplification because the acceleration is already given here, right? So F1 would be mu mg plus m times a. So what you can do is you can plug m value from there to here and you get the tension force. Now T1, how to find T1? So I will get the last equation and then subject T1. So when I subject T1, I get F minus F3 minus ma. So again, F is given as F. F3 would be minus mu mg minus ma. So again, you will get the acceleration from what you have obtained and put it here, you get the answer to that question. That's how we discuss questions with and without friction. So if you go to the first question, we have discussed all the parts A, B, C, D. Now we will consider the second question. So capital M and simple m is given. Simple m is moving under gravity g, and part A you have to find the acceleration when the surface is smooth and the tension force. Part C, the AB surface is rough and the coefficient of friction would be md. We need to find the new acceleration under that condition. Okay, so going back to the drawing board, This is how it looks like, and there will be only one rope, and it's a smooth pulley here. So simple M and capital M. So the system is moving clockwise. So mu is equal to 0 for the first part, right? So now we have to know what forces we are going to have here. So we have mg, so I will use a different color here. So T force away from the object here, T force, tension force is away from the object, and no friction. We have capital mg and the normal force R. So now we can use F is equal ma for the whole system. F is equal ma for the whole system to the horizontal direction. Now when we consider the horizontal direction, R and mg, capital mg, is not going to be counted towards the direction of motion. Why? Because the direction of the motion is perpendicular to capital mg and R. So what we have here is the only external forces. External force would be capital mg, simple mg, this one. Tension force is the internal force, is equal to mass of the system. So we use this for the system. So mass of the system would be simple M plus capital M, acceleration A. So A would be, so mg divided by simple M plus capital M. So that's the acceleration. Now what we will do, we will draw the free body diagram. That would be for capital M, it would be this. Normal force, acceleration is to the right. For the simple M object, simple mg down, and tension force T, and acceleration is going down A. Now we can use F is equal ma for the capital N object to the right direction. What we will get here, T is equal to capital M times A. So T can be found by plugging the acceleration here, which is mg divided by simple M plus capital M. Okay, so this is that. So this is tension. So that's all about that, but I will write down the equation for the simple M object as well. So that would be F is equal to ma. You're going to use for this simple M object vertically down. So the net force would be mg minus T is equal to ma. Now this time is simple ma. T force would be now mg minus ma. So I'm not going to do any substitution here. It's just a matter of putting this value over here, and that would be the answer. Now the next part would be in presence of friction, so rough surface here, and that would be mu d. So this is simple M over here, and capital M is what we had before. Okay, so now we will draw the forces. Mg here, T, and there is a friction force here, we call it Fr. So weight of the mass mg, normal force is R. So now thinking about the forces in the vertical direction on capital M, we can say capital R is equal to mg. Why? Because the system is not moving, or capital M is not moving in the vertical direction, vertical up or down. So it's just moving in the horizontal direction. So there should be vertical force equilibrium. So R should be is equal to capital mg. Now we will use F is equal to ma to the system in horizontal direction. So when we do that, what is the net force we have here? That would be mg. Don't forget, we have friction force on capital M. The total mass would be capital M plus simple M times acceleration. So acceleration can be found mg minus Fr divided by M plus capital M. And this is my second equation. Now friction force is not given, so we know by definition of the friction force that would be mu times r, mu d times r. So r is equal to capital Mg, so it should be mu d capital Mg, and that is going to be that equation. Now from equation number 2 and 3, what we can do is we can sub in the value, which is mu d capital Mg, the whole thing divided by simple m plus capital M. That would be the acceleration, the new acceleration in presence of the coefficient of friction mu d. Now we need to find tension force. What we will do now, consider these masses individually. So we have T here, Fr, acceleration this way. For simple M object, it would be mg, T, and acceleration is down. Now we will use F is equal to ma to capital M object, horizontal direction. Why? Because it's moving to the horizontal direction. So that would be T minus Fr. So T is greater than Fr. That's why, because it's moving to the right. Capital Ma. Now from here you can find T, which is Fr plus capital Ma. So Fr is mu d capital Mg plus Ma. That would be your tension force. So you can take M out from here. So you get mu dg plus simple A, and that would be the tension force. Now you don't really need to use F is equal to M to the other object, but I'll show you how to do it so that you can learn. So this I'm going to use in the downward direction. So the net force on simple M mass would be mg minus T. This would be M times A. So you can find T, that would be mg minus Ma. So you can take M out. So that would be G minus A. Now the G value you found from here, you can directly sub in, and then you will find the tension force from there as well. So now in the third question, we have the coefficient of friction given here. So simple M mass is sliding in the downward direction. So part A, if coefficient of friction is mu, what would be the applied force to keep the mass M stable without any motion? Part B, if that applied force is removed, what would happen to mass M? Give a quantitative description. Okay, so now let's start that question. So now what we will do, we will try to draw all the forces acting on this system. So now mg weight is downward, and then if you resolve it, so you have mg cos theta, this direction, and then here you have mg sin theta in the downward direction. Other than that, what you will have, right? So when this mass is not moving, okay, when this mass is not moving, we have to provide a force, P force, right? So this is the normal force, P force, where this is not going to move, right? So this is not going to move. So if there is no friction, okay, if there is no friction, P should be is equal to mg sin theta, right? If no friction, this would be P would be mg sin theta. So no argument with that, right? So now if you have a friction and you have to provide a force, but the tendency of moving would be downward, and then hence you will have a friction force, building friction force Fr in the upward direction. So now in presence of fr, what we can say, it's all about force balancing. So mg sine theta is equal to p plus fr, right? So p would be mg sine theta minus fr. So fr is nothing but mu times r, so now it would be mu times mg cos theta now, right? So p would be now mg sine theta minus mu times mg cos theta, and that's the force which is required to sort of keep the mass without moving, right? So now part B is talking about this system where you have the mass only. This mass is moving downwards with mg sine theta, right? So when you resolve it, this is theta here, so this would be mg cos theta. The weight force is mg, so mg sine theta is the only force which is acting on this. If you remove that p, and on top of that you will have a friction force in the other way, right? So the motion is this. So as I told you before, the friction force is always away, opposite to the direction of motion, right? So here if you use F is equal to ma, so parallel to the direction of motion, F would be mg sine theta minus fr is equal to m times a. So acceleration would be now mg sine theta, fr we found already, which is minus m mu mg cos theta, right? Mg cos theta, the whole thing divided by m. So a would be, you can cancel out all of this, so g sine theta minus mu g cos theta, right? And that would be the answer to the acceleration.